If you look closely at the math behind modern physics, you'll find a persistent idea that our entire visible universe might simply be a thin membrane, a single, flat, four-dimensional slice suspended inside a vast, five-dimensional void. But if an extra dimension is out there, extending infinitely in both directions, gravity should naturally radiate outward into that massive bulk, weakening to nothing here on our slice. For our physics to work, gravity has to be pinned or localized to our world. Theorists developed an elegant mathematical fix. Instead of a razor-thin, singular wall, they proposed a smooth, thick brane. By using a continuous distribution of matter across the fifth dimension, this model creates a gravitational trap, holding the graviton tightly against our surface. This built on decades of historical work regarding defect-localized matter and domain walls. The math showed that under the right conditions, you could successfully keep a particle from drifting off into the void. But holding a particle in place is only half the battle. A working model has to achieve localization, trapping the state near our brain, and isolation. It has to block the chaotic, high-energy ripples of the fifth dimension from flooding into our world. That isolation requires what physicists call a mass gap. Think of it as an energy buffer. If there is a positive threshold between the massless particles we experience and the heavy excitations of the bulk, our local physics remains protected. Without that threshold, the universe becomes a gapless continuum. The higher dimensional noise dips down to zero energy, blending seamlessly with our standard particles. The mode might be localized, but it sits right at the edge of an infinite continuum of bulk excitations. As this diagram shows, on one side you have a localized mode cleanly isolated, but on the other, the bulk energy spectrum collapses into a gapless spectrum right onto the 0 point. A rigorous class-level analysis of smooth, thick branes shows that they inevitably produce this exact failure. In theoretical physics, this is called a no-go theorem. By proving that no mathematical arrangement within these smooth boundary conditions can isolate our gravity and matter, the standard smooth brane model hits a mathematical wall. Let's look at this technical diagram. It illustrates the geometric starting point for these models, a fifth dimension treated as an open flow. The coordinate path runs from negative infinity to positive infinity, completely uncompactified. To keep gravity from escaping, the math relies on a warp factor. Looking at this second graphic, you can see how this curvature concentrates the flow of spacetime, directing it to where it intersects the flat 4D projection plane at the bottom. But this warp factor comes with an inescapable side effect, known as a universal inverse distance conformal redshift. As this 3D visualization shows, the curvature peaks sharply in the center to trap gravity, but as it fades outward toward the asymptotic ends of the fifth dimension, it decays at a precise rate, 1 over the absolute value of z. That specific geometric decay acts like a mathematical crusher. By severely stretching conformal spacetime at the infinite edges, it forces any finite mass scales residing in the vacuum to redshift all the way to 0. This chart displays the underlying metric and tensor components. The redshift isn't a glitch from choosing the wrong parameters. The Einstein equations demand it. If you have positive scalar kinetic energy and a finite Planck mass, this geometric stretching is mandatory. You need intense curvature to keep gravity from wandering off. But that exact same curvature stretches the geometry at the edges of the universe so much that the mass gap gets completely flattened out. When we run the tensor equations for gravity through this redshifted geometry, the potential vanishes at the boundaries. As a result, the spectrum of bulk modes begins exactly at 0. There is no isolated mass threshold for gravitons. This chart illustrates what happens to matter fields. When any bounded Yukawa interaction, labeled M, multiplies against the decaying work factor, the redshift forces the effective mass profile to 0 at both horizons. The fermion mass gap disappears. The failure extends to energy exchange. The equations prove that a static, one-dimensional scalar wall cannot transfer a 4-vector of mixed stress into our 4D slice. The geometry simply won't allow the transport of energy or momentum across the dimension. Finally, this graphic maps out the topological paths for phase currents. If you attempt to run a global, ungauged phase current through this stretched geometry, the gradient energy diverges. Sustaining that current requires infinite energy, which is physically impossible. The mathematics leave no room for compromise. Under standard assumptions, you cannot simultaneously have localized gravity, a massive fermion gap, and non-vanishing transverse stress. The system breaks. A no-go theorem is a diagnostic tool. By proving exactly where a model fails, it tells physicists which long-held assumptions they have to abandon to move forward. One way out is changing the slice geometry. If our 4D universe isn't perfectly flat, but curved, like an expanding de Sitter space, that internal curvature can counteract the redshift and generate a natural mass gap. Alternatively, the fifth dimension might not flow infinitely. If it terminates at a hard, singular endpoint, or loops back onto itself in a compactified shape, the continuum is cut off before it can decay to zero. Finally, physicists could rewrite the matter couplings. By using unbounded or non-minimal interactions that actively resist the conformal redshift, the mass profile could remain solid at the horizons. Smooth, flat brane models offered a clean solution to gravity's missing energy. But if an extra dimension truly exists, the math shows it won't be that simple. To protect our universe from the chaotic bulk, the true structure of space-time has to be far more exotic than we originally hoped.